So you say P controller, or sometimes proportional and integral, so you say PI controller, or P and D, which is then PD, or if all three reactions are needed, then you have your P and D. Okay? So you can, drop terms as and when you need to. So once we've looked at the benefits that each of the control actions offers, I will then look at what are the practical issues that need to be addressed in a practical implementation of PID control. Okay, and here are two of them that we'll talk about today. One is, tuning of the controller. In other words, tuning means determining the gains of the proportional action, integral action, and derivative action. Okay? So that's very fundamental. That's the starting point. We need to know the gains that will be used in the implementation of a PID controller. Then there are other issues. I forgot to include in this overview here the issue of the, problem with the derivative part of the controller, but we'll see it in the actual slides. And then, of course, one of the biggest issues is the issue of integrator wind-up. So we'll look at all this in the lecture today. Right, so this is, a block diagram representation of the PID algorithm. You can see the three channels of proportional, integral, and derivative, control actions there. So nice visualization of how to implement the controller. Now, in terms of the actual mathematics of the algorithm, this is the control law that the PID controller implements. An ideal controller, I have to say, stress at this point, and we'll be talking about, issues with the ideal controller in a minute. So, the ideal controller has contributions to the output of the controller. Variable U is output of the controller. The controller takes in the error signal, E of t, and then outputs U of t. So one part of the output comes from the proportional action. That's just a proportional to the error signal, and the constant of proportionality is the gain. So that's the proportional gain, AP. Then a second part of the control law, is the integral action part. So that part is directly proportional to the integral of the error signal over time from an initial point in time to the current time. So this is an accumulation of the error signal over that duration. And, that integral part of the control law is directly proportional to that integral, and the gain of proportionality, or the constant of proportionality, is the integral gain AI. Finally, the third part, which is the derivative part, that is proportional to the instantaneous derivative, the derivative at the current time of error signal. Okay? So the constant of proportionality is KD, the derivative gain. So you've got three things. You've got the proportional part, which looks at the present. You've got the integral part, which looks at the history of the error signal. And then you've got the derivative part, which sort of looks into the future because it is anticipatory. It is looking at the rate of change of the signal. Okay. Now, instead of using those constants of proportionality Kp, Ki, and Kd, we write the control law in this preferred form where we're only dealing with Kp and then we're dealing with integral time Ti and derivative time Td. Basically what we do is we take Kp in this first equation, factorize it out, and then you'll see that your Ki over Kp will be equal to the 1 over Ti, and your Kd over Kp will be equal to your Td. So that's the relationship between the parameters in the two formulations of the PID control law. So you have those relationships here. Ti integral time is simply the proportional gain divided by the integral gain, whereas the Td is the derivative gain divided by the proportional gain. So now, instead of using the control law in its time variable form, we transform, as usual in control, using Laplace transforms, transform into the S domains. We go from time domain into S domain. And so the transfer function relating the output, I'll sort that out later, quickly. The output of the controller divided by the input, which is the error signal, those transformed signals, when you take the ratio to get your transfer function for the controller. So it is just equal to Kp into 1 plus 1 over Tis plus Tds. So far, just basic algebra here. So nothing particularly difficult to understand there. Right. So we've looked at, what is the mathematical representation of a PID controller. Okay. Now we want to see, why do we actually use PID controller? And to answer this, we are looking at the benefits that can be derived from each of the control actions. And to do that, we'll use an example. So we take a plant transfer function, third order transfer function, and then we look at controlling this in the closed loop using, various combinations of the proportional, integral, and derivative actions. To start with, we're just going to look at proportional only control. So in this case, it's only Kp that is not 0. The other two parameters of the controller are 0. Ki is 0, Kd is 0, but remember that Ki is the inverse of Ti. So when Ki is 0, that means that Ti, the integral time, is infinite. And Kd and Td are directly proportional, so when Kd is 0, Td is also 0. So we're looking at proportional only control, which means Ti infinite, which means Ki equals 0, and Td is equal to Kd equal to 0. Okay, now I will just show the simulation response. So we look at the output response as a function of time and the input to the plant, which is the output of the controller. So this bottom plot here, this so-called input you remember is the output of the controller. Okay? And in this particular first simulation, it's only the proportional action that we're using, and we see that by varying Kp, you straight away see what effects you get with your proportional control action. First, look at the output, and in fact, that's what we concentrate on mostly, except later on when we look at the derivative control, and then we need to look at the input to the plant or the output of the controller as well. Right, so looking at the output and various values of Kp, you'll see that as we increase Kp, you can notice two things. The first is that the output response has a huge offset, in other words, steady state error, which is the distance between the final value, and the desired value. It's a unit step response we're looking at. So if there is no steady state error, the final value of the response should settle along the line, with a value of 1. Okay. Now, with the first of the 3 time plots that we show here, that one at the bottom, you see that the offset from that steady state is the largest. Okay? Kp value happens to be the lowest for the 3 plots that we've drawn there. You can see the arrow as we increase the value of Kp, then looking at just the steady state error gets reduced. So that's one of the main benefits of proportional control action. By increasing the proportional gain, you can reduce the steady state error in the system. Okay? So that's a definite benefit. But it comes at a cost, because as you can see from the plots, the first plot with the lowest value of Kp has almost no oscillations. Yeah? But as you increase Kp, you begin to see oscillation creeping in. And the more you increase the value of Kp, the more oscillatory the system becomes, the response becomes, the output response, until, if you continue to increase Kp still, you get to a point where the system becomes unstable. Unstable in the sense that you now see that your oscillations, rather than decaying, as they are in other 3 plots here, the oscillations start to increase in amplitude. So the oscillation grows. That's what we mean in control by the system is unstable. So the 2 things we take away from looking at the output response for proportional only control are: 1, for the steady state, there's a beneficial effect. As you increase the proportional gain, you reduce the steady state error, and you always want as small a steady state error as possible. Okay? Unfortunately, the second effect of proportional only control is that as you increase Kp, then you start to see the stabilization of the system creeping in. Okay? Which arrow? The arrow that has the Kp on it, that's the one that's showing you that Kp is increasing. So as you look at the 3 time plots, the one at the bottom has the lowest Kp, the one in the middle has the next higher Kp, and so on and so forth. Okay? So that's that's the arrow we're talking about. Can you understand now? Not curious? Yeah? And Eric, yeah? Eric says, okay, yeah, so that was fine. Okay, good. So those are the two effects of, proportional only control. One of them is very beneficial and it's what you're actually looking for. You can use the gain, proportional gain, to reduce the steady state error in the system. You take your KP high enough, you'll get a low enough steady state error. But it comes at the cost of, risking the onset of instability in the response. Okay? Right. So that's proportional only control. Let's now look at adding integral action. Usually you will have proportional control action, whatever you do. So the next thing is you combine it with one of the other two or with both of the other two control actions. So here we're looking at combining the proportional action with integral action. But in order to see clearly the effect of the integral control action, we'll keep the proportional control gain fixed, and then we'll vary the integral gain, or we reduce the integral time ti. But for this study, there's no derivative action, so td will be 0. And this is what you will see in this case. Again, the arrow, the black arrow with the ki on it, is showing you the direction of increasing ki. So, you start with the lowest curve. So you have 4 curves in there. The lowest curve has the lowest ki value, or the highest ti value. And then as you increase ki, you're going to the second curve, the third curve, and then the fourth curve. Okay? So increasing ki, remember, means reducing ti. So they go hand in hand. What you will now see is that I'm not sure that this is actually, I forgot to check this, but what you should see is that one is a bit of an anomaly there, the lowest one, yeah? You can see that the other 3, are moving towards settling at a value of 1, steady state value of 1, which means steady state error is 0. I think that is the original proportional only curve. Maybe it's just shown there so you can see the effect of adding ki. So that will correspond to ki equals 0, that lowest one, okay? Ki is 0, and then as you increase, ki, then you see that now the final value will match the step input, which means steady state error will not be there, will be 0. Yeah? So as long as your ki is not 0, then your steady state error is eliminated. That is the main use of integral action, to eliminate any steady state error in the step response of any system. Okay, so very, very good, benefit. One better than the proportional control, only reduces but never actually eliminates the steady state error. But then again, just like the proportional control action, you see that as we increase ki, again, the system becomes more and more oscillatory. So system tending towards instability. So we increase ki at the risk of making the system become unstable. So that's something we need to take note of, just similar to the risk when you increase AP. Finally, now let's look at, so in this case, we now have I wonder whether this is just proportional plus derivative. And yeah, this is actually proportional plus derivative. It does not include any integral action. So please make a note of that here. So this is PD rather than PID. Okay? So proportional and derivative only, so that we can see clearly the effect of derivative action. So your AI will be 0, yeah, infinite of TD will be, some chosen value that will change, yeah. Now, what you'll see here is that, no integral actions, just proportional derivative, then, no, I see. Okay, actually that's not correct. The integral action, because you can see steady state error is 0. So I roll that back. I thought it would be easier to show derivative action without including the integral. But you can still see the effect that as KD reduces, yeah, that's the direction you're going. So, in other words, if KD was to increase as well, you'll get more oscillations. Yeah. But the most important thing about derivative control action is it offers increased damping of the oscillatory response. Okay, when we increase TD, yeah, also KD, then we get better damping of any oscillatory response. That comes from the anticipatory nature. Remember, derivative control is looking at current rate of change of the controller input signal. The disadvantage of derivative action I will reserve talking about, for another couple of slides or so, okay? But you do add derivative action sometimes just to improve the damping of the closed loop system. But so we've looked at the individual control actions and the benefits that can be derived from each of them, but also noted the risks involved with the use of each one. Okay, and the most important risk is the risk of inadvertently bringing in instability of the closed loop system. So bear that in mind. All right. So now we want to now start to look at, okay, you want to implement a PID control law. What are the issues, practical issues of implementation you need to be aware of? So the first thing is noise filtering. Has to do with the derivative action in the controller. Okay, that is very important. The reason will become obvious in the next slide. Then, of course, I mentioned at the beginning as well that we need to look at how we tune the controller, how we obtain the gains to be used in the implementation. Now, some actual practical issues, problems that will be encountered include the problem of integrator windup. So we'll talk about that, today as well. We'll talk about these three issues today. The fourth issue, it's not really a problem as such, but we need to know how to, implement PID controller, digitally. As we know today, the computer is everywhere, and the microcontrollers are everywhere. So, how do you implement the PID controller digitally? So that will be the final point we're looking at in terms of practical aspects. But this aspect of computer implementation is reserved for a presentation on its own next week. So we'll be looking at that next week. But these other points we look at today. Right, so noise filtering, first of all. If we consider the ideal proportional plus derivative controller, or even, the PID controller, and by ideal, I mean, if we just go back, this is slide 13, go back to, the beginning where we mentioned the transfer function, right? So this is the transfer function for your ideal PID controller. It's only ideal, and practical implementation of this is not realistic. So to start with, one reason why it is not realistic, and that is the issue of the derivative part of the control. So the first thing is that the transfer functions, so either the PD, so that's the PID without the I in it, or the full three-term controller. In both cases, if you look at the transfer function I've just given you, you will discover that those transfer functions are improper rational functions. What that means is that they have more zeros than poles. And in practical terms, what that means is that those transfer functions cannot be realized physically, cannot be implemented physically. You cannot put together electronic components to realize them, to implement them. Okay, so that's obviously a major challenge, because what's the use if you cannot implement? Yeah. But then the other problem as well is that even if you were able to implement those, the ideal PD controller, ideal PID controller, you find that they are oversensitive to noise in the controller input signal. Okay, so what that means is they will amplify unnecessarily any noise content. And when you talk about noise, what you're talking about are the high frequency components or high frequency content in the signal. Okay, so therefore, in order to make sure that we can get around these two problems, it's necessary to modify the derivative part of the controllers with the objective, especially of limiting the high frequency gain, and at the same time being able to realize the controller physically. Okay, so remember you had KP into 1 plus 1 over TIS, and it will have just been plus TDS. But we modify that ideal PID algorithm by, multiplying TDS by 1 over 1 plus TD over NS. Okay, so we use a first order filter. That's a first order filter used to multiply TDS, and the time constant of that first order filter is TD divided by n. N we will usually take anywhere between 8 and 20. Okay? And what we find then is that if we look at the frequency response analysis of this modified control law transfer function, we will find that at low frequencies, which is where the useful content in a signal in control will be found, the modified PID control law closely approximates the ideal PID control law. So that's good. But even better is that at high frequencies, which is where your noise, the noise content in your controller input, come from, then the gain of this modified transfer function, the gain at high frequency is limited to a value of kp times n. Okay? And what that means is that, the amplification of high frequency content, or if you like, noise components in the signal, will be limited by that gain. So instead of, the ideal PID controller, which is oversensitive to noise, which amplifies those high frequency components of a signal, duly, you have the modified controller will limit the high frequency gain to that value so that it more or less, tempers the effect of the noise component in the signal. Okay, we will next week look at some MATLAB simulations which show the effect of this filtering of the derivative part of the signal. But, the concept or the idea of the whole thing is important to understand. Okay? The whole point of, adding that filter, to the derivative part of the signal is to limit the high frequency gain, okay, of the controller. Right. So now that brings us to the next issue that is important to discuss, and that is how do you tune the PID controller? So how do you, set the gains that you need for implementation of the controller? Well, the first thing to note is that all the classical control design techniques, can be applied to determine the gains. Okay? But practitioners in industrial process control over the last few decades, dating back to over 50 years ago, and when serious advances were made in process control, they relied on tuning methods which are special methods tailor-made for PID control. Okay? One of those methods is the Ziegler-Nichols PID tuning method. It was developed in the 1940s. Okay? So, all industrial control, process control engineers, that's what they use. They swear by it. Okay? The interesting thing or the useful thing about these tuning methods is that they are based on simple modeling of the process dynamics by just a few parameters. And then they use simple equations, to determine the gains of the controller. Okay? And again, we stress that these tuning rules have had major influence on the practice of PID control for more than half a century. So this is one method that is used. It's called the reaction curve method. It's a Nichols reaction curve method. Basically, to conduct an open loop step response, test of the process, okay, and that will give this blue reaction curve for the process. So that's the output of the process recorded over time in response to a step change in the input. Okay? Now, the parameters which we need for tuning, in this case, are two parameters, tau and A. And how do we obtain this tau and A? Simply find the line of steepest slope. Yeah, so you draw a line of steepest slope to the reaction curve. Yeah, remember that line is a tangent, and it's tangent to the curve around the area where the curve is. Once you draw that line of steepest slope or tangent, then two intersects give you your tau and A. The intersect on the time axis gives you your tau, and your intercept on the y-axis, which will generally be a negative intercept, is the distance A that you need, and you get your two parameters. And once you have those two parameters, Ziegler-Nichols established the rules. I've already explained this slide. The rules, which use the reaction curve method, are pretty straightforward. If you want to use proportional only controller, you simply take your Kp to be 1 over A. That's it, no Ti or Td. Yeah. If you want to use PI controller, this is how you set the gains. Kp you set to 0.9 divided by A, and your Ti you set to 3 times tau. And if you want a 3-term controller PID, then your Kp is 1.2 divided by A, but Ti equals 2 tau, and your Td is 0.5 tau. There's not very rigorous mathematical derivation of these tuning rules. They were found by, tests, trial and errors, sort of, over years of practice on what works, in process control. The TP, which is shown in the fourth column, is the period of oscillation of the underdamped step response of the closed loop system. So when you implement these controllers given in this table, your closed loop system will be underdamped, and the period of oscillation of the underdamped step response will be given by these numbers here. So as you can see, it's pretty straightforward to use the reaction curve method, Ziegler-Nichols reaction curve method, to tune a PID controller. Okay? The most important part of the tuning is finding the two parameters tau and A, which you need from reaction curve of the process to a step input. So that's one method. The second method, still Ziegler-Nichols, is called the ultimate gain method. Sometimes it's referred to as the Ziegler-Nichols frequency response method. Now, this one uses a closed loop test. Remember, the reaction curve test uses an open loop test. Okay, you do not close the loop around the process when you are determining tau and A, as discussed in the previous two slides. For this ultimate gain method, you put the loop around the process closed, so you've got closed loop control, yeah, and then you apply a unit step input to the closed loop system, and then you increase the proportional gain of the system in the controller, sorry, yeah, until you get a sinusoidal output. So you get sustained oscillation in the output response. Okay, so the input is a step input. The output, when you have the ultimate gain, will be a sinusoidal output. That sinusoidal output will have a period, TU, and the gain, which causes that sinusoidal oscillation, KU, is the ultimate gain. And the name, ultimate gain test. There is amplification, but all that is taken care of in the tuning rules. Okay. Basically, you just get this sinusoidal input. It's got some amplitude, but you're not really using the amplitude for your tuning. All you are using is the period of the oscillation of the sinusoidal wave. Okay. So the two parameters you need are your Ku and Tu values. You have the sustained oscillation. Yes, the interval, which is your period of oscillation, yes, Tu. Okay. So those are the two parameters you'll use for tuning. The gain and oscillation period, that Ku value and the Tu value, are related to the frequency response characteristics of the system, yeah, at the phase crossover frequency at point shown there. This will be a polar plot of the open loop response, frequency response of the system, yeah, and the critical point is that point where the plot or the Nyquist plot intersects the negative real axis. That point is called the phase crossover frequency. The frequency there is the phase crossover frequency. Okay, and your Ku and Tu are related to what is happening at that frequency. And how do you get your gains and so on? The way that these things are related, if we call KPC, yeah, the gain of the frequency response at that, phase crossover frequency, yeah, omega PC is the phase crossover frequency itself. Let's look at the graph again. So you've got this graph here. The frequency with the red dot, that's the frequency at that point on the Nyquist plot. The K value, which is the gain that we're talking about, K PC, yeah, is actually the distance from the origin to that point along the real axis. Okay? So that's why we say that, our Ku and Tu are related to the gain of phase at that point. Of course, the gain, what is the phase at that point? Sorry, I'm flipping back and forth. But yeah, I forgot to mention. I talked about the gain at that frequency. The phase at that frequency is minus 180 degrees. That's why that frequency is called the phase crossover frequency. Right. Okay. So now, how are Ku and Tu related to those properties of the Nyquist plot? Yeah. Well, Ku and Tu are found to be given by this. Ku is simply the inverse or reciprocal of Kpc, and Tu is 2 pi over omega Pc. So, it's straightforward, really, in terms of, what the Ku and Tu mean. And then finally, we set our controllers, yeah, as follows. If you're interested only in a proportional controller, you only need Ku value, and you have Kp to be 0.5 Ku. As usual, the period of oscillation of the closed loop system response that will result is Tp. So that's related to Tu in all cases. If you're using proportional and integral controller, then you set your Kp to 0.4 of the ultimate gain Ku, and your Ti to 0.8 of the period of the sustained oscillation that you get. Okay? And the resulting period for the closed loop, system response, the oscillation, that you will see in that response will be 1.4 T. And same goes for PID. These are the values you set for your gains. Kp will be 0.6 Ku, Ti will be 0.5 Tu, and Td will be 0.125 Tu. And then if you look at the closed loop step response, you'll see that it will be underdamped and the period of oscillation will be 0.85 Tu. So I want to stress again that, there is no strict mathematical derivations of this, but Ziegler-Nichols and other people who work with in process industries, the 40, 50 years ago, were able to test these tuned gains on several, processes, and found that they work very well. And these have now been adopted. For Salford University graduates, you will remember that you did, a control laboratory using this PID tuning rules, the reaction curve one, not the ultimate gain. Okay, so that's the second method. And then there is another method still, but this is related to the ultimate gain method, but a different test to determine our Ku and Tu. Rather than, subject the closed loop system to a step input, what we do is we replace the controller by a relay. A relay is a nonlinear element having a square wave relay function. So you have a relay in series with the process, and of course it's unity negative feedback. And by playing around with the waveform of the relay and the output of the process, you'll find that in the steady state, the process input as the relay output and the output of the process will both oscillate. The relay output in this second diagram is the square wave dashed square wave. So that's your U signal, which is the output of the relay, yeah? Which is what is then going into the process. And once the transients have died out, so you can see in the initial period here, the process output is still going through some transients. But finally that settles, and then you get a pure sine wave output from the process, okay? And that's the way the test is carried out. And again, it's very almost similar to the step response in the, okay, at least the frequency response of the process there, because the process output, in this case of the relay test method, the process output will lag that square wave relay output by 180 degrees. What do we mean by that? If you look at the traces, yeah, you'll see that where the output has maximum, yeah, the relay output has minimum. So 180 degrees out of phase, yeah. Okay, so when you have that situation, then you can calculate your ultimate gain as 4D divided by A. D is the amplitude of the relay that you use to achieve that output that is out of phase, and A is the amplitude of the process output. Okay, so you have, flip back to the diagram again, you have in this plot here, you have an amplitude for the square wave, the rectangular wave of the relay output, and then you have the sine wave output of the output, yeah. In case of the relay, the amplitude shown is 1, but in the case of the output signal, somewhere around 0.4 or whatever it is, but you can see that they have different amplitudes which can be measured. So when you measure the amplitude of the relay D and the amplitude of process output A, you use those two values to calculate your ultimate gain. Yeah, okay. Here are some benefits of this relay method for tuning. We can easily control the amplitude of the output oscillation by adjusting the relay output. So that square wave, which is the relay output, by adjusting it, to control the output of the process. So it's easy then to automate the relay tuning method, okay? And in fact, you have automatic tuning based on the relay, test method there, and that is actually implemented in many commercial PID controllers. If you go online and you just, enter PID controllers, you'll see several process controllers that use PID, from temperature control to, all sorts of other types of control there. So many of them come with automatic tuning and all the other things that make practical PID controllers possible. Right. So important thing is you will adjust the amplitude of the relay, to keep the oscillations sufficiently small. In other words, the output, process output oscillations. You don't want it too wild, yeah. But that's during the tuning. Once the tuning is completed in the automatic tuning cases, then the relay feedback is switched out of the loop and the PID controller is switched in with the tune gains calculated. So those are the three approaches to using the Ziegler-Nichols tuning rules. If you've had a look at past exam papers, I don't know if Dr. Jones has uploaded some to your content pages on Blackboard yet, but you'll find that there's always a question on the Ziegler-Nichols tuning rules. The relay method most of the time, but it will be any one of them. Okay. So we conclude that in terms of tuning, the tuning rules are very attractive and have remained popular for two reasons. One is it's easy to obtain the process parameters that you need for the tuning, and the rules, the tuning rules themselves are simple and easy to implement. That's why they can be automated. However, PID controllers which are tuned with the Ziegler-Nichols rules usually result in closed-loop systems which are characterized by poor robustness. Yeah? And that is exactly because they rely on the use of minimal process information for tuning. What do we mean by robustness? Well, when you design, you try to design for giving closed-loop system accuracy and giving, closed-loop margin of stability. Now, if you're using approximate models to do the design, in other words, to get controller gains, then, there's errors in what you've designed. It's at best an approximation, and then you'll find that you may think that you've got in frequency response balance a gain margin of 2, whereas because you've used these oversimplified process models, you actually have a gain margin of 1.2. That's just an example just to illustrate the issue of robustness. Okay, so this is something that needs to be checked if you are actually trying to implement PID controller using the Ziegler-Nichols tuning rule. You need to look at the extra issue of robustness of the closed-loop system that you have with your tuned controller. So that's the end of tuning. That then takes us to, so we've looked at the problem with derivative part of the controller. We, improve the situation by using a filter, yeah, first order filter with the derivative control part. We've looked at how we tune the controller. We look at another major problem to do with practical implementations of PID controllers. Either PI or PID. Whenever the integral action is used, this problem arises. So it's one of the most serious challenges to practical implementation of this type of controllers. Now, where does the problem arise from? Okay. In linear control system analysis and design, you simply ignore non-linearities in the system. It's not that they don't exist, but you just ignore any non-linearities and design assuming that your system is linear. Well, the reason being that we've got well-established, methods to deal with linear analysis and design. But the problem is that non-linearities are common in real systems. And so if you've designed your control system based on linear theory, then any non-linearity in the system will seriously degrade the performance of your linear design. And one common non-linearity arises from actuator saturation. Real actuators will operate below a maximum rate and or within absolute lower and upper bounds. You can think of, when we talk about actuators, we're talking of a final control element. So, for example, in flows, the valves that modulate the flow of fluid, yeah, they don't have infinite rates, yeah, and they can only open so much, so they have lower, open closing bounds. So when we talk about integrator wind-up, it is a consequence of the effects of non-linearities such as actuator saturation. Okay? So, I mentioned another example in speed control systems, for example, or position control systems, you use a motor as a final element, that's your actuator, right? And I've talked about a valve for flow control. In a temperature control, you will be your heating source. Again, there's a rate at which heat can be applied, and whatever source you are using is not infinite in terms of how much you can apply. So those are real limits on actuators. Those limits are ignored in linear analysis and design. Okay. So how does this actuator nonlinearity in an actuator affect, PID control behavior? Okay, when the control variable in the control system exceeds the actuator limits, yeah, effectively what that means is the feedback loop is broken because the actuator cannot supply what the controller is asking for. So then, during that period when the limits are exceeded, the system runs in open loop because the actuator will just remain at the limit, irrespective of what the process output is or what the controller is asking, the actuator to do. Now, if a controller uses integral action, even though the actuator is already saturated, the error will continue to be integrated. As a result, your integral term and the controller output may become so large that, first of all, you will get the actuator limits exceeded, at which point you say that the integrator is said to be wound up, or is said to wind up. So, actuator saturation or exceedance of the limits results in integrator wind up because the integrator will still continue integrating, working as if nothing is happening. So that is why we need to pay attention to the existence of, actuator saturation, which is a non-linearity in actuator behavior. When the actuator is saturated and the integral control winds up, what you see is that the closed loop response will feature or exhibit large transients, large oscillations, So that may be evidence, that will be evidence of integrator window. And unfortunately, things will, if you don't take amelioration measures, things will only return to normal when the error signal finally reverses sign and continues with the reverse sign for a long enough period for the actuator to return to within its limits. That's a mistake there, that's the form. Okay, so that is the problem of integrator windup. Let's look at a simulation which sort of illustrates this problem. So this is this simulation uses a Simulink model in which you have a first order process with transfer function 1 over 10s plus 1, but with a dead time. Okay, so it's got a non-linearity there, and then of course we've got a real actuator with saturation limits. Okay, so we can model that in Simulink. And then we've got our PID controller and the closed loop system. We're testing it for its step response. So that's just the model, that we can put together or that's been put together in Simulink to demonstrate the integrator window. Now look at two figures which highlight the issues that arise if our PID controller, does not cater for actuator saturation. So here you see two, the first figure there is showing, I think you probably can see the legend, the green curve, that's your output, Y, and the blue one is your input to the closed loop system. That's your R of T, the R signal. Okay, so what's happening here is that in the next slide, which I can put up without you losing sight of this figure. So I'll use my notes here. When the set point is 10, which is that, okay, so you're going from 10 and then suddenly you reduce to 5, yeah? The control signal will reach steady state in about 24 seconds. You see, so the change starts, the change in input is there, and you'll see that it takes about 24 seconds for the, output to reach a steady state. But it reaches a steady state, which is outside the range of the actuator. And so the actuator will be operating in a non-linear range during that period. So you will have actuator wind up. The DC gain of the plant is unity. From the Simulink model that you see there is 1 over 1 S into 1 plus S or something like that. Yeah, so the DC gain is unity. There's no reason for the controller output. No, we haven't seen the controller output yet. It will be the next one. In figure 6, the controller output is the UT there. So there's no reason for the controller output, to have a steady state value outside the actuator limits, due to the non-linearity of the actuator. But you'll see that, when the set point goes down to 5, which is at that point, then you have a considerable delay before, the system output will return to within the actuator range. And this is probably too clean, but you'll find that the actuator output, which is this is the actual actuator output, which is blue in this case, the SAT U, yeah. So you see that that's when the actuator, is at its limit, and then it takes time for it to come back to within its limits in there, yeah. The problem is this has to be taken together with that to see what is really going on. But the explanation is that the the output of the controller is asking the actuator, yeah, to deliver outside its limit, yeah, and during the period when the demand of the controller is like that, then, the actuator can only remain, at its limit. You cannot, match what is being required from the controller. Okay, and takes time for when the error signal or the input to the controller returns to, within the range that is allowed for the actuator to now start to behave within the limits. So the limits of the actuator in this particular case, I've lost my ability of my mouse to move. It's frozen. Right, so my mouse is frozen right now. Okay, so back. Right, okay, so, up to this point, we're operating in the saturated region of the actuator, in spite of the fact that the controller is demanding the actuator, to deliver that. The actuator can only actually deliver that. But once the demanded value from the controller, demand to the actuator now falls within, then you see that the actuator now behaves properly. It's delivering within its limits, and the output of the controller, then is able to respond and then settle down. Like I said, this does not actually show a very good, it's too clean. It doesn't show the bounds that you can get in real cases. We'll see more simulations next week, but this was just to explain the effect of the actuator, being demanded to work outside its range, and the time lag that it takes for the controller input to come back to within the capabilities of the actuator, and for the actuator to then function in a linear fashion again. Okay. Yeah, those are the points that I've been trying to explain there. But so what we can summarize from the, short demonstration is that when a PID controller does not cater for actuator saturation, you see the following. One, you see an excessively large positive initial error, which will result in the actuator saturating some point at the high limit. Yeah. But the integral term will also increase initially because the error is positive still, and will reach its largest value when the error goes to 0. So the actuator will remain saturated for a while because the large value for the integral term. Okay, basically the other diagram that I showed you there, where the output of the controller is demanding that of the actuator, but the actuator can only deliver that much. Okay, so the actuator therefore will not return to within the saturation limit until the error has been negative for sufficiently long enough time to allow the integral part to come down to a level and the output of the controller to be within the limits of the actuator. And like I said, that demonstration does not really show this. The actuator output will bounce between its limits several times, and during that, you'll see the plant output, showing damped oscillations with large initial overshoot. So that demonstration didn't show that particularly well. But eventually, the error will finally reduce to a level which allows it to not come out of saturation. Okay? But this can be avoided by, doing a design that takes actuator saturation, into account. Okay? But before going to that, we just note that what we've described so far is integrator wind-up coming as a result of a change in set point. Okay, but you may also have wind-up occurring due to large disturbances, in the system or equipment malfunction. So this phenomenon of wind-up was a problem for a long enough period for the industrial process control engineers to say, okay, we need to come up with strategies, to improve things. And so what they came up with are these so-called anti-wind-up schemes, which avoid the integrator wind-up. So let's quickly look at a couple of anti-wind-up schemes. If you take a PI controller, so no derivative action, first of all, the actuator saturation characteristics can be defined like this. So the controller output, will be a function of time. That should be more like commanded by the controller or asked. This is what the controller is asking the actuator. Okay, so you have the upper and the lower limits of the actuator, and so this is how the actuator will behave if the demand of the controller, is either outside or within the limits. If the demands of the controller is within the limits, then the actual input to the flange U will be, the demanded signal from the controller. Okay, so that's when we're within limits. Or if we're outside limits, well, if your the desired signal or desired actuator response is outside the limit, if it's at the beyond the higher limit, then you can only get the higher limit. Whereas if it is outside the limit but below the minimum limit, then you can only get the minimum limit. So those are the three possibilities. You can either be operating normally if you are within the limits, or if you are outside the limits, you can be operating at the maximum, actuator limit when you're above, or operating at the lower actuator limit when you are below. Okay, so you're using the usual PI controller, but you the desired by the controller is given by this. Okay, what the actuator can deliver is you. That's what the controller is asking you to deliver. That's what the actuator can deliver. Okay, so now coming to the wind up schemes. Two schemes. One is called a clamping scheme, and the other is called a bar calculation scheme. So let's take the clamping scheme first of all. The clamping scheme is straightforward. It simply says switch off the integrator when the actuator is outside the limits. That's what this is saying. Yeah. So it's saying if the controller is demanding a value higher than the maximum limit, switch off the integrator and set the demand from the controller to Umax. So the actuator will operate at its higher limit. But the integrator is off so that the integrator will not continue integrating and then become wound up. Or if it is wound up, it will take time to recover back into the within the limits of the actuator. So that brings in the sign of the error. So it's necessary to switch off the integrator in the first case because your controller is already demanding more than the actuator can deliver. But in addition to that, the error signal going into the controller is increasing, is positive. So ordinarily, the total sum, which is what the integrator is calculating, will continue to increase if you didn't switch off the integrator. So that's why you need to switch off the integrator in this case. So simple logic, if you are, demanding something higher than the actuator can deliver, and the controller input, which is the error signal, it's also positive, which will mean that the integral will continue to grow. Then simply switch off the integrator. In the second case here, we're still asking the actuator to deliver, above its maximum. But in this case, the error is going in the other direction. The error is decreasing negative. Well, we can allow the integrator to be on because we know that, the integral action will, be reducing. The integral component of the control action will be reducing. So we keep the demand from the integrator to the maximum, or we allow the integrator to continue working. Okay. Third scenario is the desired actuator, response is less than the maximum limit. Error is negative. Okay. We keep the integrator off. I think there's a problem with this. And this last two should be minimum. Can you please correct that in your notes? I overlooked. When the error signal is the error the controller demand is below the lower limit of the actuator response, so less than or equal to U minimum, and your error is decreasing, you need to switch the integrator off. But if you're outside the actuator limits, yeah, at below the lower level, but your error is increasing, so it will eventually be reducing the integral sum of total integral term. And so, eventually you will get to within the limits of the actuator. So that's why with this logic, you switch the integrator on. So the two cases where you switch the integrator off are when you are operating above actuator limit and error is growing, or if you are operating below the actuator minimum limit and the error is decreasing. Okay, so in both cases, you will never get back within the actuator limit if you do not switch the the integrator off. So that's why you switch off the integrator in those cases. So these are simple. This is simple logic that can be, implemented in a PID controller to make sure that we take care of anti-wind up, or that we have anti-wind up. This is a schematic of not a practical implementation, but a simulation. Okay, so we've got the motor drive in this case, which is this J1 over JS plus B transfer function here, and that will be the torque coming in there. Okay, now the motor has got saturation limits. Okay, now we've got a controller which is proportional integral. But we have this switch here, which will implement the logic, yeah, which we saw in the previous slide. So when we're in the outside the upper limit of operation of the actuator, if the error signal is still increasing, that switch will be opened, yeah. Or if we're operating below the lower limit of the actuator, and the error signal is negative, increasing, then again we switch that off. Otherwise, close that switch and the system will work properly. That's the clamping scheme for anti-wind up. So simple logic to implement. The other method is called the back calculation method. Okay. This shows a block diagram for a back calculation scheme for the same variable motor drive that we just looked at. The difference here is that this is not a switch off, switch on situation. Instead, what we have is there is an extra feedback loop, which you can see here, wrapped up around the actuator and the controller. Yeah? And the point of that is to improve the rate at which the U, yeah, works within the range of the actuator by playing around with Ka there. We can make the operation of the actuator within its range more easily realizable. So you have this back calculation scheme because there is this feedback in which helps in moderating the demand to the actuator from the controller. So that is our second scheme that we'll be looking at. So it's the back calculation and the what's it called, the clumping method. So that's what I've just described. The supplementary feedback loop in the back calculation scheme helps to stabilize the integrator when the main feedback loop is open due to saturation. So that helps us to quickly come back to within the actuator limits. And the point of the Ka is that we set it, so that we can improve the match between the case with no saturating actuator. So if you designed or tuned the PI controller as though there was no actuator saturation, then when you allow for actuator saturation by changing your Ka value, you can get a system that behaves similar to the system with no saturating actuator. But you got to again be careful that you do not make K too high. That's it. Right, okay, so that's how much we're doing today. As I said, we'll look at the main issues concerned with implementing PID from first. The three main issues being, modifying the derivative control part. Secondly, your tuning rules. And then thirdly, taking care of, wind up of the integrator in your PI controller. Next week, we'll look at the main issue remaining, which is the computer or digital implementation of PID control. And so, as far as my part of the module is concerned, we're more or less there. Just the next week's presentation is a much shorter one. But what we'll do next week is to look at especially, anti-wind-up schemes, simulations that go to help us understand how, wind-up looks like, yeah, and then how the back calculation method and the, clumping method, how effective they are in curbing wind up in a PI control system. So that's it for today. What I'm going to do is to now ask how far people I've got to with that tutorial that I set you last week. Has anybody had a look at the tutorial and how are we getting on with it? Yes, Eric, I think the pumpkin scheme, yeah, the logic there, those two, that should be U minimum, and this should be U minimum. I'll circle it just so it's clear. That should be U minimum, and that should be U minimum. Thank you. I'll make corrections and post the corrected versions on Blackboard after. Okay? What I'm going to do is I'm going to stop recording now. I'll restart recording for the tutorial part of the lesson. Right, so I was asking, where is, okay, I'll bring up the tutorial first. Right, okay. Oh, jeez. Press the wrong button. Take forever to get used to this thing. Right, okay, we're back there. I wanted to restart. No, I thought I pressed stop before. I didn't. No worries. I'll edit. Let's look at the second question here. How many people have had a look? Any response? Anybody? Who has had a look?
Yeah, I'm just.
STS students, is next week your last week on the in the lectures, online the lectures?
The last two.
Any STS students in the class? No response. I allowed, yeah, you can post chat messages. Okay, Eric, you first. What about the others? Right, okay. I took you through the first question last week. That's just looking at, just looking at the denominators and figuring out the poles, yeah? And if there are any poles that lie in the right half of the S-plane or to the right of the imaginary axis, yeah? So if there's any, then the system is unstable. And I think last week we agreed that the first system is unstable and the third system is also unstable. But the second system, which has two poles, with the real part of minus a half, that system is stable. But then coming to the second question, you have to derive closed loop transfer function. I did show you how to derive the closed loop transfer function last week, yeah?
Yeah.
So if the open loop transfer function, let's take part A. yeah, if the controller has transfer function just 10, so it's just a proportional controller, what is the full forward path transfer function? What is your GH of S? Yes? Okay, that's good. 20 over S into S plus 1. That's correct. Mohammed, yeah. So that's 20 over, have to use our brackets now, don't we? Use a different bracket for that one. Right, so that's your open loop transfer function actually. It's unity feedback control system, as we always assume, yeah? So then, what is our closed loop transfer function? So that's our that's the open loop transfer function. Okay. Now closed loop transfer function. Yeah, trouble is, every time you click somewhere, it think you want the text there. So what's the closed loop TF? That's not closed right now. Yeah. Well, your closed loop TF will be equal to GH of S, then divided by 1 plus GH S. So now that we have the GH of S, what is our closed loop transfer function? So, like I said, this is a tutorial class. You're doing this, and then I'll discuss what you find. Anybody wants to find your closed loop transfer function, put it in the chat. Anybody yet? No? Well, you're a bit slow, but it will be 20 over, check that out, check that you can get that. You are dividing the fraction which you get from 1 plus GH of S. You're using that to divide the fraction GH of S. If you like, do your 1 plus GH of S first. If I do that for you, then I want you to be able to do the other ones, yeah? So 1 plus GH of S equals, I'm missing one bracket. Okay. Not everything in square brackets, sorry. They also have. Okay, so when you do your 1 plus GH of S, which is 1 plus that, yeah, that's what you will get. Okay? So then, when you divide GH of S by that, remember you flip this fraction, so S into S plus 1 will come to the top, then you have at the bottom S into S plus 1 plus 20, yeah? So then when you multiply the S into S plus 1 from GH of S will cancel the S into S plus 1 from 1 to the GH of S. And so you're left with, your closed loop transfer function is equal to that. So now simplify that. So you've got 20 divided by brackets S into S plus 1 plus 20. What does that give you? Yeah, I made out the square brackets at the end of 20 here for the closed loop transfer function, but you know what I mean, yeah? So, what is the characteristic polynomial? Which is polynomial in the denominator of our closed loop transfer function. Anybody? Yeah, it is second layer, yes. Yeah, S squared plus S plus 20, that's correct. Yeah. So, if that, what are we asked to do? To determine if this closed loop system is stable or not. So, with that characteristic polynomial, yeah, this is not very interactive, to be honest. I couldn't go back to change the colors, to show what I'm saying. But if you look at this now, so the characteristic polynomial is just this one, S, because S in S plus 1 plus 20, yeah, which is your S squared plus S plus 20. So that's your characteristic polynomial. It's not stable, sorry, it is not unstable, it is stable, yeah? Right, am I right here? Characteristic polynomial. Right, so it's S squared plus S plus 20, okay? Right, so when you equate this to 0 and solve, what will be the real part? You'll get two complex numbers, won't you? Complex conjugate. Yeah? And the real part is what? Minus a half. So suppose we'll have a real part of minus a half. In fact, the full, yeah, so it is stable because the two complex poles are to the left of the imaginary axis. Okay? If I try and draw that. We'll have 1 point. The imaginary part is much bigger. And the other one here. And the distance of that line between them to the imaginary axis is, yeah, a half. So yeah, it is stable. Okay? If I ask you to find the vertical distance of the poles from the real axis, what will it be? In other words, solve that quadratic, give me the complex numbers. Yeah. (4.4i). Okay. So the vertical distance is 4.4. Yeah. We normally will write this as, this is the part I don't like because freehand writing on this thing is not my forte at all. So your, S1 and 2 will be minus a half, then plus minus what? Anybody? 4.4 you said? Yeah? Right. Check that out and see whether it is correct because to calculate it, it's actually square root of 20 minus a quarter. Square root of yeah, it's about right. It's precisely, it is square root of 79 divided by 2. Square root of 79 is what? Then divide that by 2. Okay? So, that's finding the poles of the closed loop system. Yeah? But all you need for stability is the real part. Where does it lie in relation to the imaginary axis? So in relation to this imaginary axis, if your poles are to the left, the system is closed loop stable. If any, not necessarily all of them, if any one pole is to the right, then the system will be closed loop unstable. Okay? Right. So, we've gone through A in detail. Now, you should be able to now do the rest of them. First, find your open loop transfer function, then your closed loop transfer function, and then figure out the characteristic polynomial and the location poles. Okay? So I want you to finish that before next week. Yeah? And then next week, I'll only, respond to people who may have had any issues with question 2. But mostly I want to go to question 3 and question 4 next week. Because for S tier, how many people are S tier in the group? How many? If you are not going to be participating in, well, I think the timetable lectures will end after next week, won't they? In which case, we have no tutorial classes or anything again. So I don't know how that will work out. Yeah. But yeah, I want to look at these tutorials next week in preparation for the examinations, especially the STS students who do their examination a bit earlier. Yeah. So it's important that we go through these tutorial questions. Like I said, next week, lecture itself will be a short one, probably about 40 minutes, 45 minutes, and then the rest is tutorial. Well, examination for STS students, Dr. Jones is the best person to ask for that. Yeah, Dr. Jones will give you details. I'll tell him to give you details, maybe send an email or an announcement, yeah, about your examination. Yeah. Okay. So that's it for today, ladies and gentlemen. So keep working on these tutorials and go through. Well, you will do your own exam in January. Krishna? Okay. So, yeah, non-STS students, your exam is in January, but STS students, I think your exam is earlier. I'm not sure exactly when. Okay. Right. So I'll see you guys next week. Cheers. Thank you. Bye-bye.